Bam! Mr. Taru. In this math lesson, we're going to be talking about composition of functions, introducing what that means, and working through 3 examples. You'll find timestamps in the description below to jump ahead if you so desire. We're going to have example 1 where we have a couple of functions and we'll be setting up f of g and g of f and discussing the domain of our compositions and comparing that to the domain of our original functions along the way. We'll be doing f of g of 2 with an algebraic type example. We'll be doing the same type of example when we are given a graph of function f and g, and we're going to be analyzing f of g of -3. And you'll notice that notation is a little bit different than this notation we have up here in example number 1. Our third example is going to be looking at a function h of x is equal to the quantity of 2x minus 5, all of that cubed. And we're going to try and break that apart and instead of bringing functions together through composition, kind of like undoing that composition and discussing a little bit why we care about that kind of last example. So here we go. Composition of functions. We have function f, which is equal to 1 over x, and g of x, which is equal to 1 over x plus 4. But I picked this because I want to have a good conversation about the domain of the parts and the final composition function. So we have f of x is equal to 1 over x. Well, the domain of a function. When you go to find the domain of a function, you're looking for what values of x can you plug into a function and have that function give you real solutions, real values. We're not going to be discussing, like, say, imaginary numbers in this video, and certainly not values that are undefined. So anytime you have a function with division in it, you should be cautious of, okay, there are some things I've been told many times in my math classes that such as you cannot divide by 0. You can have 0 in the numerator, but you cannot have 0 in the denominator. You cannot divide by 0. Even 0 over 0 is undefined. It's a form of indeterminate. It's a little bit special, but here we have a denominator. F of x has a denominator of, well, x. And so what is going to make that entire denominator of x equal to 0? Well, there's not much going on. It actually is 0. So for f of x, our domain is going to be all real numbers such that x cannot equal 0. And in g of x, we have a division of x minus 4, or excuse me, x plus 4. That entire expression, all of x plus 4, is in the denominator. So it's not that x cannot be equal to 0, it's that the entire denominator cannot equal 0. So the entire denominator of x plus 4 cannot be 0. Thus, when you add both sides by 4, you have x cannot be equal to -4. And that's the only number that we cannot plug into the denominator. That's the only value of x that is going to, real value of x, that is going to cause this denominator to be 0. And again, you cannot divide by 0. So our domain of g of x is all real, now to pick a different color here, all real numbers except that x cannot equal -4. And we're going to keep that in mind. The domain of f of x is anything but all real numbers except x cannot equal 0. And g of x, the domain is all real numbers except x cannot equal 4. We're going to keep that in mind as we talk about our compositions coming up here. So in part A, I'm going to show my work here and then kind of write the answers as I go. A says to figure out, calculate, if you will, f of g of x. And I am personally not a fan of this notation at all. When you have an open dot between two function names, that does mean composition. It's not a closed dot. It's not like I'm doing, you know, f dot g. That would indicate multiplication, or when those two names are touching. There's an open circle in between those two function names. And not only can it be very easy to kind of scribble that up a little bit and think that it's, you know, with your handwriting a little bit sloppy and have it look like multiplication, but I don't feel like it gives a natural setup or notation of telling you what to do. So I like to write this as f of g of x. And this is the notation I much prefer. And we have an inside function. Let's see, hopefully orange shows, I think orange usually shows up pretty good on the camera. We have the function g going inside the framework of function f. And that's how I like to tell my kids to do compositions. When you see f open dot g, I will always write it as f parentheses g of x, and the inside function g is going into the framework of function f. So this composition means the first letter is the framework. And function f of x is, yes, it says equals 1 over x, but in terms of substitution, especially when you're working on plugging in expressions, instead of saying 1 over x, I like to say it's 1 over something. A variable is just an open spot to put something into our equation. So our outside function is function f, which is 1 over something. Nothing wrong with where I put that parentheses, but I'm trying to emphasize the variable of x is in the denominator. That's the open place that we're putting something. And then in that open place, we're putting the inside function g. G is going into function f, and g is 1 over x plus 4. So let's make these parentheses a little larger. And put in the function 1 over x plus 4. Now, if it's been a while since you've seen a fraction divided by another fraction, in class, once I've been working with my students enough, I kind of just do like a little squirrely line indicating that I'm going to multiply by the reciprocal. But this is read as the numerator of 1, and I'm going to write that as 1 over 1 so that we can have the numerators and denominators line up in our next step. But that's going to be 1, the numerator, divided by the denominator of 1 over x plus 4. And while we write divisions of fractions, we really don't work with division of fractions. We actually multiply by the reciprocal of the second function, or the second fraction, excuse me. Which of course has given us an answer of x plus 4. So f of g of x is equal to the composition of the function g, 1 over x plus 4, going into f of x, 1 over x. That final answer simplifies down to be just simply x plus 4. Now, if we talk about domain of this composition of f of g of x, if you now at the end decide, let's determine what the domain of this composition is, this basically new function, you're going to see that we have x plus 4. This expression shows no division, no even root of a potentially negative number. It's just an algebraic expression. We're not doing trig and natural logs and stuff like that yet, but there's no restrictions here. It looks like our final answer has a domain of all real numbers. Now, your textbook, in terms of finding domain, the rules for finding domains of compositions, it'll tell you to first find the domain of the function going inside, the second function, the function going inside the other function, and then determine the function of your composition. But here is where you want to determine the domain of your composition. It's before you simplify. We already know the domain of g, which end up being that inside function, is all real numbers except x cannot equal 4. Even if I hadn't already checked that, if I look right here at the first line after setting up the composition, this is where you want to determine where the domain is before you simplify the composition. Now, in this unsimplified form, you have this entire fraction in the denominator. Well, this entire fraction potentially could be equal to 0. So we'll go back to, well, I've already used orange. Let's use green, I guess. This entire denominator of 1 over x plus 4 cannot be 0. Well, the only way that a fraction can equal 0 is if the numerator is equal to 0. And since our numerator is 1, a constant, that's never going to happen. The only way that we have that this entire, the only other restriction we're going to have on domain is, okay, this entire denominator of 1 over x plus 4 will never be 0 because the numerator is equal to 1. That numerator will never be 0, but we have another division inside that denominator of 1 over x plus 4. Of course, we still have that division of x plus 4. That's what set up the restricted domain for g of x. So the composition of f of g of x does have still have a domain of all real numbers except x cannot equal 4. And I'm just writing a restriction for space purposes on my board. Don't try and find the domain of a composition after you have simplified, because that will lead you to potentially giving a wrong answer. Y equals x plus 4 is just a line with a y-intercept of 4 and a slope of 1. Lines have no discontinuities. Their domain is all real numbers. But that's not when we check domain. You check domain the instant you set up the composition. That's where you check domain before you simplify. So let's see what part B is going to look like. Okay, so for part B we're asked to figure out what is g of f of x, or in other words, a notation that I like to use, what is g of f of x? And it is that g being the first letter in our composition, and it's this way in this, it's the first letter in this way, this particular form of the notation as well, and f is what is going on the inside. And I wish I remembered the color coding I used in my previous example, but that g is the first letter we see. That g, function g, is the framework. And then into that framework we will substitute in the function f of x. So what's the framework? What's g? G of x is equal to, well, 1 over something. There's a variable there, so something is going to go in its place. So something, open that up with a set of parentheses, plus 4. And then what is going into that something? F of x. And f of x is 1 over x. Okay, so we have a little bit of work to do. We have 1 over x plus 4. 1 over x plus 4 is in that denominator. Now we are going to find domain, but I'm going to go ahead and simplify this right now. There's two ways of simplifying this. You can, and I think I do want to show you both ways. More tools in your toolbox, the better and more creative you can be with your subsequent problems and sections within and journey in mathematics. You can find a common denominator, because right now you have a big old division sign and it is a numerator divided by all the denominator. But I'm not going to write this fraction, this complex fraction, side by side and flip the denominator up right now, because if I flip that whole denominator up and try and multiply by that reciprocal like I did in the previous example, we would be skipping the common denominator process of bringing these two terms together, and that will give us a wrong answer. But we can add these two fractions in the denominator. We can have recognize that the first fraction in the denominator has a division of a division of x, and our second term is 4 over 1. Multiply 4 over 1 by x over x, giving us 1 over, now with that common denominator, we're going to have 1 plus 4x over x. And now that we have that main division bar and only one fraction in the denominator, we can show that multiplication. Now this time I'm just going to actually write the multiplication of the reciprocal for purposes of space. And we have the numerator of 1 over 1. So I have the numerators and the denominators line up correctly, over x over 1 plus 4x, or in other words, our composition, g of f of x is equal to x over 1 plus 4x. Excellent. Now, if this is what we look at to determine the domain of this part B, we would be saying, okay, hold on a second. In terms of domain, we have a denominator that is equal to 1 plus 4x. So 1 plus 4x cannot equal 0, so 4x cannot equal negative 1 after we subtract both sides by negative 1, and x therefore cannot be equal to negative 1/4, which is true. And by the way, we would get the same answer if we went to set this denominator equal to 0. Yeah, so it looks like our domain is all real numbers, except that x cannot equal negative 1/4. Well, let's not forget, actually, let's turn our attention back up here. If we look at the entire denominator and set that entire denominator equal to 0, we will have that restriction on the domain of negative 1/4. But inside all of this denominator, of 1 over x plus 4, you also have a division of x. So in that unsimplified form, you have an entire, you have a fraction bar, so you have that entire denominator can't be equal to 0. And then within that entire denominator of 1 over x plus 4, you have another fraction, another division of x, and that also cannot be undefined. You cannot plug in 0 for x because you'll have 1 over 0, which is undefined, and then you can't add 4 to something undefined. You just get another undefined value. So either in unsimplified form of the composition, we can see that there's two restrictions on the domain of x cannot be 0 and x cannot be negative 1/4, or we have that restriction of the inside function right off the bat when we figured out f of x does have that restriction on the domain that x cannot be 0. So again, with compositions, always look at the unsimplified form to find the domain. Don't simplify everything first and then find the domain. Or if you do simplify, know that you need to go back. Now, I haven't forgotten that I said I was going to show you an alternative way of doing this example. And that is, yes, you can take the two terms in the denominator, find common denominators and get that one single term in the denominator and then multiply by the reciprocal. But I would be willing to bet that most of you are going to be happier with not dealing with that fraction that we have in our composition, that complex fraction, but actually getting rid of it. In the numerator, we just have a constant of 1. But in the denominator of this complex fraction, we have a division of x. Fraction bars are just division symbols. And if you want to get rid of that division of x, you can do so by multiplying, and we're going to multiply because multiplication is the inverse to division. Multiply the numerator and denominator by x. So you have one term in the numerator, so we only have to multiply once. You have two terms in the denominator, so we're going to have to do that distribution or multiply twice, distribute the x to two different terms. That is going to give us 1 times x is x over, now x times 1 over x, if you're showing every single step, is x over x, and then 4 times x is going to be 4x, and there's our same answer of the composition is x over x divided by x is 1 plus 4x. A little bit less work. Just multiplying the numerator and denominator by a factor which is going to cancel out that fraction bar or that division symbol. So that is part B, along with the domain as we move through these examples. Now, in part C, we just have another composition here, but now instead of an x, we have a number. And how do we deal with that? Well, since we have already figured out the composition of f of g of x, and we know the expression, our simplified expression here is x plus 4. Since that's already done, we can just take that f of g of x, or f of x of g, no, hello. Since we already have that f of g of x, which is x plus 4, we can just plug the 2 in and have, well, 2 plus 4 is equal to 6. And it's just that simple. But maybe you haven't already done the composition. You could work out part C, and this is going to help us with the graphing portion as well. We can work out part C as, and I'm going to go back to my favorite form of composition notation, which is f of g of 2. And here's kind of why you need to check for the domain of the inside function first, and then check the domain of the final composition, or just set up the composition and check domain before you do any simplification at all. That 2 has to go into function g. So I could just go, hey, you know what? Let me just do this in pieces. What is g of 2? G of 2 is going to be 1 over 2 plus 4, which is going to be 1/6. And then step 1, that inside function is done. Now let's step out to function f, and that's going to be f of 1/6. Remember, 2 is going into function g, and then from g of 2, we're getting a y value. We're getting an answer from that function, which, well, g of 2 is 1/6. So now f of 1/6, well, function f is 1 over something, and that something we're plugging in is 1/6. And here we go again with the review of dividing by fractions. 1 over 1/6 is 1 divided by 1/6, which is going to be equal to 1 times 6. which is equal to, hey, look at there, the same answer, 6. Whew, this is fun. On our second example, chalk down, we have, or maybe it's called the fourth example, but over here on our graph, we kind of have the same thing where we have a picture of our functions, not the actual equations to work with. And how do we evaluate f of g of -3? Now here, we kind of have to go through that operation that I just erased. We don't have a simplified version of the composition that we just plug our number into, and that does actually cause a lot of confusion with kids. And this is really just, these kind of questions are really just testing your knowledge of just the notation. We hardly have to do any math. We just have to understand that with function notation, we plug in a domain value, generally it's called x, and we get out a range value, which is generally what we call y, even though of course that's not required. So reading the graph, and let me get a piece of yellow chalk here. What is the value of g when x is -3? Well, when x is -3, and g is the white graph, when x is -3, excuse me, when x is -3, function g is giving us an answer of 2. So -3 goes into g, out comes an answer of 2, and now we're doing f of 2, which simply means we need to look at function f, which is now the orange graph, go to an x value of 2, and identify the y value, and the answer is going to be 4. And that's our second example. Now for our third example, or maybe the fifth example, depending on how we're counting, but I have it labeled example 3. We have find two functions f and g such that f of g of x is equal to h of x. And one more time, I'm going to change from f open dot g of x to be f of g of x. Now, when you deal with compositions, again, it's what's that inside function, which I think I did blue every time. So that function, inside function, is g, and that outside function is f. And honestly, problems like example 3, you could argue have many different versions of answers, but in terms of the classes I teach, which are pre-calculus, pre-calc honors, calc AB, calc BC, and higher level math in our international baccalaureate program, compositions are important for you to identify. Well, in just algebra 2 and pre-calculus, you might be just identifying transformations of functions. And in calculus, we would be talking about, we talk about taking derivative of composition of functions, or derivatives of compositions, and we actually integrate compositions. Now in terms of the derivative side, this isn't calculus yet, so I'm going to just say, hey, you might want to look up something called the chain rule. When we find derivatives of functions and we can identify that there's a function inside of another function, we have to go through a process called chain rule. So it's really important that we can see a composition of two or more functions coming together, where functions are being put into other functions. And really even though there's many answers, the simplest thing is just to look at the outside of, the most outside math function. It might be a big square root, it might be natural log, it might be a sine function, but what I'm looking at here, because we're just at the beginning of pre-calculus, or maybe you're in an algebra 2 class, we have a set of parentheses, and then outside of that, we have a power of 3. So the power of 3 is being applied to a base that's not just a simple x. The power of 3 is being applied to a base that kind of has a lot going on inside of it. Inside this power of 3, we have a variable that's getting multiplied by 2 and a subtraction of 5. If I were talking about graphing cubic functions with transformations, the factor of 2 that is on the x would be a horizontal compression, and the minus 5, whether it's written parentheses, the quantity of 2x minus 5 raised to the third power, or as I would prefer if I were talking about transformations, I'm not going to focus on this too much because then I'm going to have kind of like a composition of three functions instead of just two. But we could write this in terms of transformations of functions, 2 parentheses x minus 5 over 2, and all of that being cubed, where my outside function is a power of 3, so I can still look inside of here and look for what transformations have occurred or have been applied to the parent function of just y is equal to something, x cubed. And there's a value of a, which is going, a value of 2, which is going to be a horizontal compression because 2 is greater than 1. And then with that coefficient of x being 1, we have a graph that's been shifted to the right 5/2. Okay, I'm doing a lot of rambling right now and not giving you an answer because I'm trying to make you understand the importance of questions like this, even though it might seem a little bit simple, but I've color-coded this a few times. We have an outside function of something, a base, being raised to the third power. So f of x is equal to x cubed, and what's inside that power of 3 is our g of x, which is equal to 2x minus 5. And while there arguably are other correct answers, there are other functions that you could do compositions with and create h of x. Keeping it simple is usually the best way, and in this case it certainly is. I'm Mr. True. Bam! Go do your homework.